I'm director of Scientia, and we're delighted that you're with us for the inaugural lecture of Sciencia's 2021-22 lecture series. It's great to be back in person. Each year, Scientia brings together outstanding Rice faculty to examine broad themes that transcend disciplines. This year's series celebrates and explores the vast interconnectedness that animates nature and human life. Tonight, we're honored to present Professors Paul Padley and Jacob Robinson. Paul Padley is a professor of physics and astronomy and the director of the T.W. Bonner Nuclear Laboratory and has been with Rice for over 25 years. He is internationally regarded as a leader in particle physics and currently leads the United States contributions to the operation of the compact muon solenoid detector at the CERN Large Hadron Collider in Switzerland. He is also a fellow of the American Physical Society. Paul is also currently serving as professor, as Rice Interim Vice President for IT and Chief Information Officer. He holds a PhD and master's degree in physics from the University of Toronto and a bachelor's degree in physics from York University. Jacob Robinson is an associate professor in electrical and computer engineering and a member of Rice's Neuroengineering Initiative. His research group uses nanofabrication technology to create miniature devices to manipulate and monitor neural circuit activity. He received a BS in physics from UCLA in 2003 and a PhD in applied physics from Cornell University in 2008. Following his PhD, he joined Harvard University as a postdoctoral research fellow in the Department of Chemistry and Chemical Biology. He joined Rice in 2012 as an assistant professor in electrical and computer engineering. Dr. Robinson works on many collaborative projects with partners here at Rice, Texas Medical Center, and is a performer on several multi-institutional DARPA programs to develop neurotech and bioelectronics. He currently leads a DARPA-funded team to create non-surgical neural interfaces, named Moana after his daughter's favorite movie. Dr. Robinson is the recipient of the DARPA Young Faculty Award, the Materials Today Rising Star Award, and is the senior member of IEEE. He's also former co-chair of the IEEE Brain Initiative and a core member of the IEEE Brain Neuroethics Working Group. Each speaker will speak for about 20 minutes, and then we'll open the floor for questions for about 10 minutes. And for those of you in person, please join us in the lobby for a reception afterwards. We're thrilled that you're here, and please join me in welcoming Paul Padley.
Thank you. It's wonderful to have an opportunity to come speak to an audience in person and not have to answer questions about I/O, which is how I seem to spend my time these days. But today I'm going to talk about connecting the small and the big by connecting people. So let's start with, what do I mean? Of course, it stops working now after testing it. IT issues. Okay, so what do I mean by the small? I mean infinitely small. Okay, the fundamental particles of nature, like electrons, quarks, things like that, they're presumed to be infinitely small. We've made measurements, okay? So for example, we know that quarks are smaller than this number here. Okay, so when I'm talking about small, I mean really small. And when I'm talking about big, I mean as big as it gets. I mean the universe, the entire universe. And what I want to convince you of and talk about is how you can't understand the physics of the big without understanding the physics of the small. So let's start with the big. So the universe is uniform. On average, when I look out in any directions, all directions on big scales, it's uniform. And that's consistent with there having been a Big Bang. There's lots of reasons why we think there's been a Big Bang, but one of the features of a Big Bang is you get a uniform distribution of matter spread throughout the universe. Okay, so that's an observation. But we also know the universe is not completely uniform. I'm a lump in the universe. You're a lump in the universe. This room, the Earth, stars, galaxies, they're all lumps in the universe. So that structure had to come from somewhere. You wouldn't expect that structure from a Big Bang. So how did that come about? You can even take pictures of the structure. So this is the Sloan Digital Sky Survey, and this is a map of a big chunk of the universe. And you can see there are dense regions, less dense regions, voids, and so on. So there's a lot of structure in the universe. And so the question is, where did that come from? We can even look back to the universe using something called the cosmic microwave background, and we can look back in time to the time when the universe was 380,000 years old. And when you look back in time at that universe at 380,000 years old, you see the structure in the universe. So something's going on that seeded it very early in the lifetime of the universe. So it's a dichotomy. We expect the Big Bang to give you a smooth universe, and the universe is pretty smooth, but it does have structure. And we want to reconcile those two observations that seem to be, at conflict with each other. And the way this is done is something called inflation. It's not the inflation that Janet Young worries about. It's what's called cosmic inflation. And the idea is that the universe started in a Big Bang, and at any point in space and time, there are quantum fluctuations. You may have heard of the Heisenberg uncertainty principle. This allows you to violate momentum energy conservation for very brief amounts of time. And so you can get fluctuations in the vacuum. And the idea is, when the Big Bang started, these quantum effects, these microscopic quantum effects were taking place, and that's what seeded structure in the universe. And then the universe expanded faster than the speed of light. Now, I first heard about this when I was a graduate student in the 80s. We were sitting there thinking, oh man, that can't be right. The universe. But in fact, it's a key ingredient. It's what's going on there, okay? Because when the universe expands faster than the speed of light, the bits of the universe become disconnected from each other. They can't communicate. So while we can't send information faster than the universe, that's exactly the key ingredient that we need. Okay, so those fluctuations in the universe, in the early universe, get frozen out by this rapid expansion of the universe. Okay, so the structure in the universe is seeded by that when the universe is very small. We have this inflationary epoch where it blows up very rapidly, and you freeze those out, and that's what seeds the structure. There's a whole history of the universe that we can talk about. This is a scale you're probably not used to seeing. The inflationary epoch is sort of less than 10 to the minus 32 seconds old in the age of the universe. And then the first few minutes of the universe is a whole chain of events that happen that give rise to the structure in the universe. And all these things are happening on subatomic scales. If you look here, you'll see, here's when protons were formed in the early universe. So everything that's going on in this period of the universe is with stuff that's smaller than a proton. And that's the stuff of particle physics, which I study. Here's a simulation of the effect. When scientists model what this effect would be, you see the universe, you let it evolve, and you look at what comes out. You actually get something coming out that looks kind of like the structure of the universe. That gives you confidence that there's something to this idea. So the physics of the very small is deeply connected to the structure of the universe. Okay? And then that takes us to what I do. So I do research at the Large Hadron Collider, and we try to understand the physics of the very small with extreme precision so that it can be used to further our understanding of the universe and the Big Bang and all of that sort of thing. Okay, so the basic idea of what we do there is we smash protons into each other and watch what comes flying out. We basically use E equals mc squared to make the heavy particles, the heavy stuff that would have existed in the early universe. It's like taking two strawberries, smashing them together, and getting out a bowl of fruit. And that's what we do with subatomic particles. It's a big experiment. It's a big accelerator. It's circular. It's 26 kilometers around, 100 meters underground. And the experiment I'm on is over here somewhere. I can't spot it at the moment right now. Okay? There are two big experiments, Atlas and CMS. I work on the CMS experiment, so we'll talk about that. To give you a sense of scale, here's an office building at CERN where we have offices and meetings. These are the two experiments. So they're the size of a building, these experiments. In fact, to give you an idea of the size of our experiment, here it is, a full-scale picture of the end of looking down the end of the experiment. Okay, you can see it's many stories high, it's about 5 stories high. And here are a few of the physicists who work on it. If you can find me in that picture and I'm there, I'll buy you a beer. At Rice, we have 5 faculty members who work on the experiment. And that plus postdocs and engineers and grad students who are all working on it. Okay, and these are big, weighty experiments. Notice in this picture, this is a blown out picture of the experiment, there's a person for scale. This experiment weighs 12,000 tons. It's got more steel in it than the Eiffel Tower. Okay, it's a big thing, and it's packed full of electronics. Here's a picture of it being assembled on the surface. It was assembled in pieces and then lowered underground. There's a 1,900-ton piece being lowered down a detector, a piece of detector being lowered down underground. You could ask, how do you lower a 1,900-ton piece of equipment? Very carefully. Okay, here are pieces arriving underground, and then they all got shuffled around and put together. Okay, many important people have visited the experiment. Here's Stephen Hawking when he came to pay a visit. Presidents of universities have come to visit the experiment. Like I said, this experiment is packed full of electronics. Okay, so there are 145 million channels of electronics that have to be read out every 25 nanoseconds, every 40 million times a second. That's being read out. So imagine a camera with 145 million pixels running at, taking pictures 40 million times a second. And that's the amount of data we're producing. Here's an example of the stuff flying out. I told you, like that bowl of fruit, there's all the particles flying out from that collision. Okay, remember this picture is a picture of something that's 5 stories high and longer. Okay, some more pictures of the events as they happen in the detector, the stuff flying out. And you can zoom in and see all the mess of what's going on. And we try to work through all this data and figure out what was going on, because what was going on then is connected to what was happening in the early universe. Okay, and just, if there are any, we're in an engineering building, if there are any computer people here, the raw data rate out of the experiment after you suppress zeros is about 80 terabytes of data a second. Okay, so imagine 80 terabytes of data a second coming out. So we've made some big discoveries. Our most famous big discovery to date has been the discovery of the Higgs boson. The Higgs boson is a fundamental particle. It plays a real critical role in the formation of the universe. It's the particle that gives fundamental particles their mass. Higgs and others won a Nobel Prize for that. We got an honorable mention for making the discovery. Okay, and it's a new tool for discovery. So we're just embarking on our research. Now that we're making Higgs bosons, we're trying to study them in detail. There's a big effort to do that so that we can connect it to the structure of the universe and what's going on there. There's other ways we can make tests about the universe by studying things in the microscopic scale. One of the favorite ones I like to talk about is extra dimensions. So it turns out if the universe had more than the 3 spatial dimensions and the 1 time dimension, if they had microscopic extra dimensions, really interesting things could happen. You can maybe unify the forces with gravity, which we can't do at the moment. And if you do that, if you get energy collisions happening at high enough energy that you're probing that extra dimension, you can do things like make microscopic black holes, which sounds really scary, but in fact they would just evaporate, they wouldn't do anything. In fact, if we made microscopic black holes, we would know that there were billions of them created up in the upper atmosphere and they haven't hurt us, so we know it's safe. Okay, and so we can do simulations and we can look in the data and see if we see evidence for that. Well, we don't see evidence for that, or I would be here giving a different talk. Okay? But the point is, as Einstein told us, our experiment is able to test the space-time structure of the universe. Okay? So there's lots of really interesting things we can do. I can't possibly get into it. We've produced over 1,000 papers to date. Obviously, it would take more than 20 minutes to explain all those results. There's a worldwide effort to analyze the data and produce the results. And then there's a worldwide effort to connect what we learned from the experiments to the theory of the early universe. There's a big worldwide efforts underway. It takes a village. Our experiment, CMS, has around 3,000 physicists on it, including graduate students, 1,000 engineers, hundreds of technicians, 229 institutions, including Rice, in 51 countries around the world. Okay, so there's this huge community of people working together, all connected together, working together to analyze the data and produce physics results. And then there's a worldwide community of theorists, 2 of whom are here at Rice, pictured here, who are trying to take the results of those experiments and connect it to the physics of the early universe and cosmology now. So it's a huge challenge, is how do you connect all these thousands of people around the world to work together on a physics project? Well, there was a little invention we made along the way, people working at CERN. This is the first example of a web page. So the World Wide Web was invented at CERN in first proposed in 1989, invented in 1990, and distributed to the particle physics community in 1991. And I played with it in 1991 and had no clue as to why this would be useful. It took a couple of years until the Mosaic browser came out, and then it was like, oh yeah, this actually could do something. I think we can say that we've had an impact with that invention. And that's actually, this ties into a key part of the mission of the science we do at CERN. Okay, so if you look at CERN's mission statement, it's to provide a unique range of particle accelerator facilities to enable research at the forefront of human knowledge. That's great. Perform world-class research in fundamental physics and unite people from all over the world to push the frontiers of science and technology for the benefit of all. Okay, that's the underlying mission. Actually, CERN was created in Europe in the 1950s because Europeans had basically just spent a lot of time trying to kill each other, and it was thought this was a way to get people to work together on common scientific goals, for the betterment of humankind. And so in some sense, for me, that's the greatest accomplishment of our field. That, the greatest accomplishment in particle physics is we're connecting people around the world from many different countries and cultures, often countries and cultures that are in conflict with each other, to work towards advancing our understanding of the universe. And for me, that's our greatest accomplishment. So I'll end there.
Okay, hello everybody. Hopefully you can hear me. Okay. At least in the room you can hear me, because I can hear myself. All right, we take a moment to try to connect, and this is always a challenge. No matter how long the pandemic lasts, I will never figure out how to share my screen. Well, thank you, the organizers, for putting this together. I think it's a really fun topic. I had to kind of rephrase what I normally do. And before I get into the details, and I'm confident I'll probably rush at the end, I want to acknowledge the people I'm going to talk about today. I have the fortune of being able to work with a fantastic group of students and postdocs here at Rice. We're going to take a little snapshot of a little bit of the work that we do. I can't talk about what everybody's doing. The stuff I'm going to highlight is work done by Amanda Singer, who recently graduated as a postdoc with us, Josh Chen, new graduate student Josh Woods, my close collaborator in ECE, Kai Wang Yang, and his student Zhang Hao. So these are the people who did the hard work. I get to come around and tell stories about it. And the story today that I want to tell is inspired by our theme of connections. So my lab works on connecting devices to our brain. And if you follow the news, perhaps you know that Elon Musk started a company in 2017 to connect our brains to computers. In July of last year, he took to his favorite social media platform, Twitter. Thank you for that, Paul, and CMS for putting the internet together. So we have access to the thoughts of billionaires like Elon Musk. And he took to the platform and he said, yeah, I'm going to connect your brain to a computer and allow you to stream digital music to your auditory cortex. And us in the neurotech community, we're like, hold on. That's crazy talk. And in some sense it is. We don't have the knowledge of the brain in order to really make that possible. The technology doesn't quite exist yet, not to mention the fact that there are regulatory hurdles that we'd have to go over if we were to be able to make this possible. But I wanted to take this inspiration, or I wanted to take this idea as inspiration for thinking about what the future might look like if we could connect to our brains to computers. What's the work done here at Rice that might make this possible, and where might we be in the next decade? Spoiler alert, you are probably still going to listen to Spotify with your headphones, but I want to think about what might be something we would see in the next 5 to 10 years. And to get started with that, actually, it's okay to pick this off. I'm having a hard time. All right, so to get started with that, I want to think about what current brain implants do today. So brain implants today are medical devices. Okay, so you can't just plug something in your brain so you can watch YouTube. You need medical need. And here's an example of a woman who has Parkinson's disease, and what she has implanted in her brain is a deep brain stimulator. And what that deep brain stimulator does is it silences the tremor that she has. And so when it's turned on, you can see her walking through the hallway. When it's turned off, she has a halted gait because she can't control the way that her body moves. And the way that this deep brain stimulator works is it's one electrode that's turned on typically in the subthalamic nucleus, a deep brain structure about 6 inches deep in your brain. And it's connected by a long wire to this implant here that looks a lot like a pacemaker. And in fact, in some sense it is. It's an implanted pattern generator, and it has all the electronics to control that pulse sequence. Okay, so Elon Musk wants to stream YouTube and listen to music. This is what we have today. And as effective as this is, I think this is just the beginning of what we might be able to accomplish with these devices that we can connect to the brain. There's an article that came out on Monday in the New York Times about a woman who had major depressive disorder, and her symptoms were alleviated by the exact same type of technology. The same type of deep brain stimulator put in a different part of the brain helped her in ways that pharmaceutical therapies could not. Now, this was an N of 1 study, so nowhere near the number of collisions that you would see at an experiment like LHC. One person participated in the study, and that became the research paper and the article in the New York Times. When we look at Parkinson's disease, typically less than 10% of people who are eligible for that implant opt to go through that procedure. Many more people could be helped by that and choose not to. And going on beyond just major depressive disorder, there's clinical trials underway for obsessive compulsive disorder, Tourette's, epilepsy, Alzheimer's, addiction, pain, any number of therapies that we have a really hard time treating with pharmaceuticals could potentially be treated with these type of electronic therapies, and yet so few people enroll. I think a big reason why that is the fact that this procedure is pretty dense. So, there's an electrode here, like I mentioned, that goes into the brain, and this whole thing that fits on the palm of your hand, about the size of an Oreo, gets implanted in your chest, and a wire gets run up through under your skin. And so if you can imagine, you're suffering from Parkinson's disease or depression, the idea of going through such an invasive procedure might be one of the reasons why you hold off on doing that, despite the fact that you could benefit from such a procedure. And so as an engineer, this is where we look at it, is okay, maybe there's an opportunity here. Could we make something smaller, safer, minimally invasive, that could provide those same kinds of therapies? And that's what we're doing. One of the things that we're doing here at Rice is to take what looks like something the size of an Oreo and shrink it down into something the size of a Tic Tac. So how do we do that? Let's unpack this a little bit and understand the engineering challenges. So if I were to break open that implanted pattern generator, we would see that the largest components are actually this battery here and a capacitor. So the things that store energy. The electronics are relatively big, but actually these can be shrunk down pretty small, and these connectors are actually a big piece here. And so the device that we're building in the lab right now, I'll show you guys a prototype, is what we hope will be the smallest human brain implant. It looks something like this. It has many of the same pieces. You'll notice electronics, a tiny capacitor, but you'll notice no battery. You'll see no connectors. Because we can make this thing so small, we can put it in the part of the brain that needs therapy. And instead of a battery, we have this thing called a magnetoelectric antenna. Who's heard of magnetoelectric antenna? Put your hands down, Doug. All right, I'll come back to you. So there are probably very few of you, and the reason why is because we don't use them very often. Why not? To understand that, I want to talk about submarines. Our bodies are mostly salt water. Right? So, okay, how about I ask you another question? Anybody seen The Hunt for Red October? Okay, thank you. Thanks, Doug. You put your hand up. Right, so the whole premise of this movie is they're like trying to escape Russia. No one can talk to Moscow because they're underwater, right? They're underwater, and the ions in the ocean prevent you from transmitting electromagnetic energy. So we can't send power, we can't send data through the salt water. It's the same problem inside of our bodies. We are trying to communicate with these submarines, but the electromagnetic energy cannot get there. So instead, we've been looking at this idea of using magnetoelectric antennas, or this process called magnetoelectricity. And the idea is that magnetic fields, unlike electromagnetic waves, can penetrate into the body, can penetrate through salt water. And so what we do is we connect, or we fabricate, we make these materials that vibrate a little bit when we apply an alternating magnetic field. And that vibrational energy gets transferred into an electrical potential, or electrical energy. So this material converts magnetic fields that penetrate into an electric field that can power our implanted electronic device. So there's a few of the audience who are physicists who raise their hand perhaps recently, might look at this and say, we already have ways to convert magnetic fields into electrical potentials, and it's just inductive coupling, and that's what we use for everything. And that is true. My iPhone, I can charge on those power mats, right? It's because I have a magnetic coil that captures that magnetic field. And in fact, you may also argue, this seems like it would be a lot more efficient just to use a coil. You don't have to like vibrate anything and lose that energy and all that kind of stuff, and you would be right. Except for one small detail. That small detail is the fact that the scaling of these two power transmission methods is very different. So if I look at how much voltage I can generate from this coil that I have in the back of my iPhone, it depends on the size, the area of that coil. But this magnetoelectric material, it doesn't matter how large the area is, only the thickness of it. So what that means is I can make these things smaller and smaller and smaller and still capture a lot of power. This is, I think, the unique insight in why our iPhones and basically nothing uses magnetoelectrics for power. It's because we haven't been trying to power millimeter-sized devices inside of our body. So there's a unique opportunity for us. And in fact, when we look at how much power we get, we see that indeed this inductive coupling is a lot better until we get to the small size scale. And then there's a crossover point. This might not look like much. This is a log scale, but we're talking about factors of 2 to 5 to 10 in terms of the power efficiencies. And we get other factors that push this up to about a factor of 10. So we can get 10 times more power into these little tic-tac sized devices inside of our body for the first time. And based on this idea, I think we're beginning to build a platform for what I hope will be this future way of connecting our brains and bodies to computers to perhaps do a better job of treating depression with a minimally invasive procedure. So I'll show you a little bit of that, what that looks like today. This is a rat. This rat has Parkinson's disease, or at least a model of Parkinson's disease. And just like the wound that I showed you at the beginning, we're going to have Parkinson's only in half of the body. So when this rat goes to try to run around, one side will be coordinated, the other side will not. And you'll see that it kind of runs around in a circle. Now what we've done with this rat is we've also implanted the first battery-free deep brain stimulator. No battery. It captures all of its power from the magnetic field. And you'll see that when we turn this device on, the rat no longer spins around in a circle. So we created that same therapeutic benefit that we saw the woman walking through the hallway using something that fits on the head of a penny. We're taking this a little bit further now in the lab, and we realize that this is a resonant effect, which means there's one frequency where we get the most amount of power to our device. And that means that if we shift that frequency just a little bit, we change the amount of voltage that we transmit. And that means that we can also send data to our device by simply slightly changing the frequency of that magnetic field. So we can have these digitally programmable, we can transmit wireless data and power into these miniature devices. And what that means is that I think we can develop minimally invasive programmable stimulators. Stimulators that might be so small they can fit within the blood vessels in your body and be delivered percutaneously, non-invasively driven up perhaps through the femoral artery to targets in the spinal column, where you might want to use them to treat pain, perhaps all the way to the central nervous system. So imagine having a neural implant without ever having brain surgery. We began to build these devices and test them with our colleagues over at the Texas Medical Center. Peter Kahn is a vascular neurosurgeon, and this is one of our devices here shown up on, and you see it on X-ray. This is implanted in the femoral vein. You can see it here in surgery. And what we can do is by delivering devices through the blood vessels, we can reach targets in the spinal column that are common targets for pain therapies. So one way, if you suffer from chronic back pain, would be to stimulate that nerve. And that would typically involve having spinal surgery, which is a pretty invasive procedure. People often don't opt for it for the same reason they don't opt for the deep brain stimulators. What we can do here is show that we can stimulate that nerve from within the blood vessels, avoiding any spinal surgery at all. And we know that it's actually working because this nerve also controls the chest wall. So you can actually see in this animal model for this procedure, which is a pig, you can see that chest wall contracting each time you turn that stimulator on. And so what was exciting about this is it's the first time that people
Dr. Robinson, the 10% figure you mentioned about people who opt for the device now, that really seems low even for. I mean, is there any evidence of why that is? I mean, were there adverse effects that they're talking about?
Yes, excellent question. I'm not aware of any solid academic literature that understands why this is the case. When I've participated in working groups with neuroethicists and patient advocates, the things that I hear are, this idea of putting something inside your head is kind of scary, right? So that's one aspect. The other is the efficacy of the procedure maybe isn't as high as it could be. So if I could guarantee that it would work every single time with very few adverse side effects, I think you would see more adoption. And that's the third angle, is that there are adverse events. A lot of them relate to the fact that there's this long lead wire that connects the implant to your IPG. That's a pathway for infection. It's also where the most common failure point, something like 20% of the procedures fail due to something going wrong with the lead. And that involves having to have another surgery to come in and fix it. So I think the things that we think about are minimal invasiveness, better efficacy, and then fewer adverse events.
Great talks, guys. Jacob, I'm just curious, how much actual power do you need to draw? Because I really like the magnetoelectric antenna idea. I just wonder about whether there are other effects one could exploit, pyroelectricity, thermal electricity, and stuff like that.
Yeah. It depends on the application, obviously. For our purposes, we typically think about a milliwatt. Average power is what we need for these devices for stimulation. We want to be able to do more things. So I kind of hinted at this idea at the end of closed loop, where we can record what's happening inside the body, use that information to then stimulate something. The recording requires even more power. So what we found recently is that with the same millimeter-sized devices, we can get closer to tens of milliwatts. What's slightly interesting about this, forgive me for going off on a tangent for 1 second, is that when we think about inductive coupling, right? I have one loop of wire and another loop of wire. There's very little I can do to optimize that efficiency. But with the material, it turned out that our first materials weren't as good as they could be just because the material isn't as good. If I could have something that vibrated a little bit better. So the fundamental limits are actually a little bit unknown. That's why we're pushing up to tens of milliwatts at this point. Exactly. Yeah. So I think there's a really interesting space for thinking about engineering this as a platform for power delivery just in that small form factor.
Any other questions?
Paul, I have a question about exceeding the speed of light. So I've always been taught that you can't because things become infinitely heavy.
expanding faster than the speed of light is space-time. Okay, and that's blowing things apart. So you can't really think about, me running away from you, going faster than the speed of light. It's actually the space between me and you is getting bigger and bigger. So I'm not moving through space any faster. It's the space that's moving. Okay, so that's the. So you have to think of space in terms of the Big Bang doesn't just create the material of the universe. The Big Bang creates the space-time that the universe is in.
Okay, we do have a couple questions. Okay, couple questions. So Dr. Jason Hafner, he says, it seems that the next step for the neutral devices is to get information back from them. Do you have any ideas of how you could do that?
Wonderful. I love that physicists asking questions. Okay. Yes, we do. We've been thinking hard about it. Thanks for the question, Jason. Let's see, what can I say about it? It is a solvable problem. I think we are, maybe as much as I can say about it right now in public, it's possible. We weren't sure when we started this project if we could get information back. And it turns out that there are a couple ways of doing it by exploiting the Magnetoelectric effect itself. The other way of getting information back is by transmitting data back using another modality. That one we're actually pretty far along on. And the idea is that, if I take that submarine analogy, right? I try to get a lot of power because I need to power my device. That doesn't mean that all the energy is lost on the way going down, but most of it is lost, so I'm not getting very much power down my input. But for recording data, I don't need a lot of power coming back, I just need enough to capture a signal. So I can transmit data using one of these highly attenuating modes like light or by using an inductive coil. And this mixed mode modality is what we're doing right now. I think there is a future for using magnetoelectrics itself for getting bidirectional communication.
I want to ask, I'm a sociologist, and I want to ask Paul a social science question, if that's fair. So I wonder...
as long as it's not IO.
I wonder if you can help us hypothesize as social scientists, what are the kinds of conditions that are present in these large scientific collaborations that connect people that we might then try to replicate in other kinds of social environments? As you know, I've had the privilege of spending time at CERN, and it really is amazing to see people.
So I think it's a great question, and it's a question I know that I remember as a postdoc having sociologists coming around asking us these questions, late 1980s and that. It's an outstanding question, and I've never quite figured out what makes it successful. So when I was a graduate student, I worked on an experiment called Argus. It was incredibly productive. Made some big discoveries that were really important. In a 2-year period, there were 50 of us working on the experiment, and we produced 50 papers. Okay, so incredibly productive. Many of those same people went to work on another experiment called Hera-P. It was a bigger experiment, but the same leadership, many of the same people, and it was a total disaster. And I remember the leader of Hera-P, who had been the leader of Argus, talking to me at a conference, and she said he couldn't figure out what it was that went wrong with that collaboration that made it dysfunctional, whereas his previous collaboration had been so incredibly productive. So I don't know that that's well known, but certainly evidenced by the 1,000 papers we produced, we found a way to be productive. And you've been to CERN and you've seen what goes on. It's fair to say not everybody's getting along either. It's not like it's a big happy family. I mean, CERN came out of the ashes of war, and sometimes, you still feel the tensions in the room with the cultural differences and that are there. And somehow, so I guess I'll give a partial answer. We do have a common goal, right? We're working towards a common goal in a very broad sense. The detailed goals we're after might be different, but the goals are common. And so I think that's a key element So, imagine Doug's job as chair of a department where there's everybody wants to do different things in that and you're trying to get cohesion. I think that's an incredibly hard job. At least in a big experiment, it might be 3,000 people, but it's 3,000 people who are sort of committed to this idea of studying the very small to understand the universe and cosmology and how the universe came about. So there's this underlying common goal there. So, yeah, okay. But it doesn't always work. Why is that?
Wonderful. Let me take a question from online. Barry Willett asks Dr. Robinson, I heard in the news recently that these stimulators may be being used with people with the opioid addictions. These addictions were eliminated overnight. Is that true?
I'm not familiar with that particular report. I do know that neurostimulators are being used for the opioid epidemic in at least two ways. One is treating addiction, and the other is actually treating pain using non-addictive therapies. And actually what I showed you guys in terms of that nerve stimulator is funded by the NIH as a non-addictive alternative to opioids. So I think there's actually two angles that people are taking, and I think both treating addiction as well as treating the pain directly, non-addictively, are definitely opportunities.
So for Paul, Professor Padley, I was very struck by the unified nature of the universe at the very large scale and the very small scale, and the way that it seemed like matter is kind of there at both levels and is very structured at both levels. But I was kind of wondering, why is there so little matter? Like, why did the Big Bang kind of send out this splatter of stuff that seems to be so relatively rare compared to space?
So, in fact, there's a whole big problem that we don't understand, and I just didn't make it a topic for discussion today, which is actually, when we talk about matter, we have to, so because of E equals mc squared, energy is like matter, okay? And actually, if you look at the energy-matter density of the universe, it's mostly dark matter and dark energy, and we have no clue what that stuff is. Okay? No clue whatsoever. We know it exists. We can do gravitational lensing and all kinds of measurements. We can measure the expansion of the universe. So we know there's dark matter and dark energy there. And what I didn't tell you when I showed that simulation of getting the structure of the universe right, you don't get it right if you don't put in the dark matter and dark energy. So your question is great, and it's 10 times, 20 times worse than what you thought, because actually it's, of the stuff that's out there, it's dark matter and dark energy. If you get a good idea about it, let me know so I can steal a Nobel Prize from you.
Wonderful. From Benam Azam, if we consider three modalities, I think this is for Dr. Arminson, invasive, minimally invasive, and non-invasive. They all have their challenges and potentials. Which one would you bet on?
All of them. And I have to say this because he directs the neuroengineering initiative. So yes, we should bet on all of them. I guess we should answer that more honestly. I am betting on one of them, and that is the minimally invasive approach, because I think that there is a huge space between what you can do from outside the skull and what is being done with current highly invasive devices. Then it's really a continuum between the two, right? So things that might be delivered through the blood vessels that don't cause a hole in your skull somehow feels different to people. And so I think that falls into one category of something that's minimally invasive in the sense it goes to the blood vessels. What about things that might involve an injection? Or in the future, if we're willing to do things like gene therapies that are actually already in clinical trials, it's a level of invasiveness, but it's not fitting neatly into one of the two categories. So I think that what we're going to see in the future is expansion in terms of this space between the deep red stimulator that I showed you there and what is going to be done externally.
Dr. Padley, this is sort of a follow-up on the earlier question. What cultural differences have you seen that helped or hindered the research you're doing with over 50 countries? Have you been able to overcome them?
Well, I'll take 1,000 papers as evidence that we've overcome them. Okay, so we'll take that right there as a given. judge different cultures, but different people take different approaches to things. So in one culture, you may be more focused on doing the work and getting it done, and in another culture, you may be focused on laying out a very clear plan of how you're going to get that work done. And so you may have one group of people who are doing very careful planning, plan out in advance every step of what they're going to do, and in another culture, they may just be, let's just dive in and do it. Somehow they both get to the same place at the end, following their different paths. And actually seeing that happen is interesting to see and terrifying to the people who don't belong to the other culture. Right? So you can literally be in a meeting where you can just see the tension rising because of these different approaches to solving a problem that's going on. And that's just one axis. There's lots of different ways about that. Some cultures might, when they're writing a paper, be more fluid in the language that they choose to use. And another culture might be more, terse and to the point. So somehow you all work together, and all our papers end up sounding like they were written by the same person.
Wonderful. Thank you. Any other questions in the room? Yes.
This is a question for Jacob. I am a humanist and English professor, and so I'm going to ask you the humanist question. And that really focuses on what you might predict as being some of the ethical challenges or implications of these really kind of remarkable discoveries you're making.
Yeah, I'm glad you asked that question. I was hoping I was going to get it by meeting with this Elon Musk anecdote. That's a whole other research field in some sense. I mean, so I can tell you my personal experience. We recognize huge ethical implications of our work early on. Right? I mean, the devices that I showed you today are not ready for human use, but we know that one day they will be. And so what we wanted to do is think about what are the ethical implications well in advance of beginning our first human trials. And so as a group of engineers in the space, we've connected with societies like the Global Neuroethics Society and the International Brain Initiative has a neuroethics working group. And we began to have a conversation with the ethicists. And what I think is, so there's a lot of really interesting things that I've learned in this process. And I think your question is specifically what are the major categories. I think the things that come up a lot are privacy. Who has access to the data that comes out of the brain, who controls what goes in. Autonomy, that kind of touches on that second thing. Do I have control over my device? Who has control over my device? How do I regulate that? There's other questions about access, which I think is a really big one. Right? If we start to develop technologies that might improve human performance, who benefits from this? Is it just the wealthy? How can we make devices that are accessible to everybody? We don't want to create further widen the class divide between the haves and the have-nots, because now there's expensive technology that can make you smarter or remember things better. The other topics, bias is the last one. So one thing we're looking at carefully is that as we develop these technologies, are they going to perform equally well in people of all backgrounds? When you think about, and there's evidence of this coming from tech in other areas, and we have a small group of people developing technologies that don't often think about the needs of others and the performance of the devices when you start to apply it to a broader population. There's actually, ironically, Facebook is now funding work to look at addressing some of these ethical implications, including bias. For example, the technology that they're developing is based on optical interfaces, and it turns out optical interfaces are not well designed for people with high melanin content or thick curly hair. And so these are the kinds of things that we want to kind of address early on, so that we don't develop these technologies that work great for rich white people. Right? And then I think there was one other point that I wanted to make on the ethics front. And I think I lost my train of thought. Anyway, that's maybe enough to work with. Sorry for going on, but yeah, excellent question.
Wonderful. Well, thank you so much.
Can I interrupt?
Oh, yeah.
None of the students up here asked a question, so we shouldn't end until some of the students ask questions. Yeah.
Just kind of going off of the fact of ethical or the ethics behind it, how people are going to receive something like you're developing. I know COVID-19 played a huge part in adding distrust to health system. Do you think people are going to continue to have those fears? The whole vaccines or implanting, all those crazy things. But do you think that that's going to in any way affect the development of what you're doing? Or
based on the emails that I get, I would say it already has. Yeah, in fact, I learned recently on YouTube that some of our technology currently is in the COVID vaccine. That's a joke. This is not in the COVID vaccine. But there are conspiracy theories out there that these technologies are doing. So yes, it has affected us. I think it will continue to affect us. I'm hoping that some smart people will figure out how to bridge that divide. I would have to, I guess, have some faith in the younger generation that helps solve these problems.
Somebody from the back section. Yep, there we go.
So, at the beginning of your presentation, you brought up Elon Musk and Neuralink. And while you explained that, so at the beginning of your presentation, you brought up Elon Musk and Neuralink. And obviously, the technology isn't there for us to, have some basic promises. However, what kind of ramifications do you think that has in terms of, do you think there's any, positives that come out of that, rather than just empty promises?
Excellent question. So to rephrase maybe for people online, the question is, what are the potential ramifications for people overhyping the technology beyond what is going to be deliverable? And is there any advantages to that? I've had a lot of discussions with my friends in neurotech and neuroscience, and I tend to be more of a tech optimist, and I do see benefit from what Elon Musk is doing. And I'll give you my argument for that. He's brought a lot of attention to the field, and it's inspired a lot of creative and ambitious people to enter the area to fund new technology startups. There's a lot of extremely talented engineers that are working at Neuralink that are coming from top academic labs, and they have now opportunities to then take the next step, which we all hope as academicians, is that what you have in the lab will one day make it out and be available to the broader community through commercial devices. And so those are all really positive things, I think, that come out of the attention of the kids. Obviously, there's negatives, and negatives are backlashes. And I think the one that I'm maybe most sensitive to is the idea that there are people suffering from conditions that are optimistic that next great thing is almost there, and they will sometimes hold off on opting for a therapy with the idea that, Neuralink is going to be able to cure my deafness in a couple of years, or they're going to cure my blindness, and so I'm not going to opt for this other clinical trial. And then at some point their hopes, are going to be dashed when they fail to deliver. So I recognize the pluses and minuses with that, but I think and I'm glad that you and others are aware of the double-edged sword of this.
Well, I want to. Question. Go ahead. Last question.
Yes. Could you kind of elaborate on the importance of space expanding above the speed of light, and how that kind of free?
Yeah. So I didn't want to get too technical, but let's get a little bit more technical. So if I have a big bang, I expect stuff to be smooth. Intuitive quantum fluctuations cause things to be not smooth. But if I have two things, so what happens when I take something out of the refrigerator? It warms up and it comes into thermal equilibrium with the room. It comes to the same temperature. And in some sense, you can think of these density fluctuations as temperature fluctuations. It's sort of equivalent when you look at the physics. Okay? So if you can have communication between between these different areas. It's just like they'll come into thermal equilibrium. So you might have started with ripples in space-time caused by the quantum fluctuations, but if the universe is expanding slowly, they're going to come into thermal equilibrium with each other. So they're all going to end up being uniform. It's all going to end up being uniform. Just like the thing you took out of the refrigerator comes to the same temperature as the room around it. Okay, so that's the problem. So the key is, if you expand faster than the speed of light, those things can't exchange energy or information anymore. And so they can't come into thermal equilibrium with each other. And so that's what I mean when I say frozen out. Okay? It means they don't come into thermal equilibrium with each other. And that's a key ingredient. Up until Alan Guth had this idea, nobody could actually solve that problem. And this provided a solution for that problem.
So if I'm understanding correctly, we only have a universe because we didn't have connections right at the beginning.
Well, we had connections that then got blown apart.
Okay, blown apart. Well, thanks to Dr. Padley and Dr. Robinson for wonderful talks. Thank you all for being here and your great questions. Thanks to those online, and please join us for the reception afterwards.